Welcome to this episode of the Structural Engineering Channel podcast, a podcast focused on helping structural engineering professionals stay up to date on technical trends in the field and to help them succeed in their careers and lives. In this episode, we're talking to Kevin Moore, who is the senior principal / division head at Simpson, Gumpertz, and Heger, and Erica Fischer, Ph.D. PE, and an assistant professor at Oregon State University. I'm your host, Matt Picardo. I'm a licensed engineer at DCI Engineers, practicing on structural projects in California, with an undergraduate degree from Cal Poly Pomona and a master's degree in structural engineering from UC San Diego. And now I'd like to introduce our guest for this episode. Firstly, Erica Fischer. Erica Fischer, Ph.D. PE, is an assistant professor of civil and construction engineering at Oregon State University. Dr. Fischer's research interests revolve around innovative approaches to improve the resilience and robustness of structural systems affected by natural and man-made hazards. She has participated in post-earthquake reconnaissance team missions in diverse regions, including Haiti, Napa, California, Italy, and Mexico City, and post-wildfire reconnaissance in Paradise, California. Kevin Moore has experience designing, evaluating, analyzing, constructing, researching, repairing, and investigating healthcare, commercial, institutional, and residential facilities. He is nationally recognized in the field of seismic performance engineering with experience in California healthcare facility development, specializing in the seismic evaluation, design, and construction of general acute care hospital buildings. Kevin is also a recognized expert in structural steel design and construction with unique experience working with special steel moment frames and buckling restrained brace frames. He's the chair of the National Council of Structural Engineer Associations, or NCSEA, Seismic Subcommittee to the Code Advisory Committee, and is the NCSEA representative to the Building Seismic Safety Council. Now let's jump into our conversation of the week. Erica and Kevin, welcome to the show. We briefly introduced you to our guests earlier on the show, but in your own words, can you please tell our listeners a bit about what you do on a daily basis? Erica, why don't you go first?
Sure. So I am a professor at Oregon State University, and so that means that I'm doing a combination of teaching and research and service to the professional community on a daily basis. So I teach courses on structural engineering concepts to undergraduate and graduate students. And I do research on gaps in knowledge as it pertains to infrastructure performance during natural hazards, such as an earthquake or a wildfire, what we're here to talk about today. I'm also a member of many professional committees, and so I get to interact with Kevin on the NCSEA Resilience Committee, and I'm on the board of directors of ERI. So just kind of balancing all three in my daily basis.
Great. I'll take over from here, I guess. I'm not nearly as interesting as Erica. She's just a dynamo, and so glad she's on my committee. So I lead our structural engineering group in the San Francisco Bay Area. Simpson, Gumpertz, and Heger has approximately 38 people or so there. And as a nationwide firm of almost 600, we have quite a bit to do in terms of the management. So that keeps me a little busy. I also develop my own practice and maintain that, do client works for clients, and that ranges all over the map from new design to evaluating existing buildings. The day-to-day, like Erica, I spend a lot of time not only on my day job, if you will, on those things that help bring in some revenue for the company, but a lot of time on associations and volunteer efforts. I'm currently the vice president of Structural Engineers Association of Northern California and pretty active on NCSEA committees, and even am involved in code development. So currently right now we're finishing up the balloting for ASCE 7, which is our base standard for the design we use in the structural engineering profession.
Awesome. Thanks for those quick intros, guys. Before we jump into the wildfires, we want to give our audience, just let's talk about resilience, because I think that's kind of the bigger picture, and then we can jump into that. So Kevin, can you tell our listeners what resilience is related to buildings and structural engineering?
Sure. So resilience is related to a community. And so buildings, of course, are stagnant. They don't move. They don't, they're static. They can't actually respond like people or communities. So resilience is really all about the recovery of a community. And we have done a bad job about getting that out to the public and making sure people understand that it's not just a buzzword. It does have meaning, especially in a planning context. And so we as structural engineers or in the structural engineering community that provide built structures really establish, I'll call it little rocks. And so if you were to think of a flood kind of taking over a basin, maybe Death Valley actually gets filled up with water again, we would create little islands that actually do very well in the face of that flood or in an earthquake or something like that, that the community could respond to and have a safe place or a local place to actually gather and contribute to their recovery. So if you have your buildings falling down, it's very difficult to recover. If they're still standing, then you're able to deal with that. And of course, everything in between has something to do with the repair of the damage. So we as structural engineers contribute to the resilience effort. We don't actually get an opportunity to lead it or do something different about the buildings that they repair themselves. Although that would be cool. And maybe Erica will figure out some ways to do that with some new materials or something.
So basically resilience, and correct me if I'm wrong, it's basically the recovery after a major catastrophic event or some damage. Basically, if the building's falling down, obviously that's not resilient, but maybe the building takes less damage maybe during an earthquake and you can repair it quicker, or it takes no damage. Is that kind of what the gist of it is?
Yeah, so in our context, we know structural engineers, we know performance. We know about designing a building, so that's what we call life safe. That's been going on for decades. And that is really to understand that the building, when faced with a large event, whether it be an earthquake or a flood or large winds like a hurricane, the building doesn't collapse and damage the interior and bring risk to both the occupants and significant inability to recover. So that's our first goal, is make sure that we don't have any life risk in our buildings. The second goal is to try to minimize the amount of damage. And that is so you have a place to live, or you have a place to work, or you have a power plant that functions. And so we think about functionality. We think about trying to design a building that has a high likelihood of being operational or functional or immediately occupiable after an earthquake. And we have all of those tools and definitions within the structural engineering community that works in the seismic realm. And we've been working on that since probably about 2000 is really the seminal date that we started thinking about functionality and how it is that we provide buildings that do a little bit better than life safety. And actually they do a lot better than life safety. And our building codes have been improving over the years. Since 1997, we have continued to refine the building code. We're not worried about buildings falling down anymore at all. If there's a new building design, most of us don't think that that's ever going to be an issue in anything like an earthquake or a hurricane if it's actually followed the building code and built per our designs. But they get more refined. The details are better. The buildings are tied together better. We're using more accurate, what we think to be more accurate definitions of hazard. And Erica will explain that a little bit, because wildfires are kind of new in the world and we still have to figure out how to define the hazard. So all of those things are what we consider. And so we then contribute a piece of that puzzle, and that resilience, that ability for the community to recover, is really dependent upon how quickly you can get back to normal. And we actually, our NCSA Resilience Committee is writing a paper currently that talks about that concept and actually indicates that maybe getting back to normal looks a little different. And for those of us that are living through the pandemic now, and hopefully this is seen 20 to 30 years from now and people don't have any idea what we lived through this last year, back to normal is kind of a different scenario for us. We'd just be happy to get outside and maybe attend, go to our offices or attend an in-person concert or something. We don't have very high demands right now. We're pretty happy with getting back to semi. So we call that adaptive resilience. And that is the community controls what it means to recover. Not us as structural engineers, and not a book, and not a planner or a government, but really what society thinks is reasonable. And the government, if they're doing their job, will actually identify that, oh yeah, that works, and we'll fund things to get us back to that level. So resilience actually has nothing to do with what we do in structural engineering, but everything to do with how communities respond. And so we want to make sure that people know, like, we know that, and this is what we contribute to it best. So I know it's a long answer, and I apologize for that, but I take every opportunity I can to kind of set everybody's expectations in alignment so that we can actually deliver something that's anticipated. Because if we show up and say, oh, we can make your building resilient, then people expect it to recover and when it doesn't after an earthquake, then we get in trouble. So we're trying to make sure that people have the right expectations, and planners can use us. And that's how we get to be a little bit more useful.
Yeah, thanks for that. Yeah, I appreciate the in-depth explanation, because it is something that's the term that's used a lot in our industry, and sometimes you'll just hear it, but you may think one thing, but with your clarifications, really appreciate that. Erica, why would you say resilience is important for structural engineers to consider?
Just build off of what Kevin has said. He just laid the groundwork so well. Our infrastructure doesn't exist in a vacuum. So we don't just build bridges just to have the structure there. It's all based on functionality. Our infrastructure is serving a function for our community. And when it doesn't serve that function, we don't have resiliency. So, as Kevin was talking about, we don't really worry about buildings absolutely falling down if they're designed with modern building codes. However, the behavior of our sprinkler lines, of our partition walls, of our gas lines are all dependent upon the acceleration displacement of our structure. So our structure has implications that just ripple through the community. If a building or a hospital doesn't have access to water, then it can't be functional, right? So I think sometimes we forget that our structures are great, and it's so much fun to design them, but we're designing them and we're building them for a purpose in our community. And all of this infrastructure is all connected to one another. So you might have your isolated building, but if that isolated building is next to an older building, and that older building is heavily damaged, then we might not be able to be functional in our hospital or school or whatever it is. We saw that pretty prevalently in Napa after the 2014 earthquake. And so as structural engineers, our initial gut reaction might be, well, the structure performed really well, but did the structure perform really well so that the building can maintain its functionality? And so, an example of this, I was trying to think of an example for when you gave the questions, but I was in Mexico City after the 2017 earthquake. Our team visited a hospital, and it was standing, and it just had minor damage. And we're all talking, oh, this is so great. This is such a great example of this hospital standing and doing really well. And the ground motions were really strong here. And, the community was, this community was pretty much decimated. But the director of the hospital kept going on and on about this one masonry infill wall that was leaning slightly out from the structure. And so we go back and we look at it and we go, yeah, it's leaning slightly out, but we don't think it's gonna, fall over. And he pointed out that the gas lines were attached to this infill wall, and without gas, they couldn't do laundry. So a hospital needs clean sheets. They need cleanliness, right? So this kind of goes back to, our profession has gotten to the point where, yeah, we can design our structure not to fail, but we have to go that extra step now and to say, can it function after the disaster, after the earthquake or the hurricane or the wildfire, to make sure that it can still serve the community. So just to kind of build off of what Kevin has said there.
Yeah, great example, Erica. Yeah, like you're saying, what's the point of a hospital if it can't function when we need it the most, and if it can't be a hospital, it's kind of just a shelter. And well, during those disasters, that's when you need the hospital operating fully functionally, and even though it didn't have damage, well, it's not too resilient, like you're saying. So that's a great example. Kevin, I just wanted to get clarified something here, because I know sustainability is also kind of thrown around a lot now. What's the difference between resilience and sustainability in your words?
So the sustainability idea has been around much longer than resilience. There's, as Erica indicated, there's some major earthquakes that have happened around the world that make us think about this ability to recover as a community and function in the face of an event. And earthquakes have been kind of lightning rod for that. So as we evolved resilience, it felt good for people to put the two together. They thought it aligned, and to a certain extent it does. I don't mean to dismiss that completely, but the concepts are so different that you don't want to get them intermingled and designed for sustainability when it has a potential effect on the response or the ability for the building to basically function after that earthquake, as Erica explained. And that's, kind of at its core, as Erica did a great job of layering on all the importance of the infrastructure within a community. So, even stuff well outside of buildings, like, large pipelines and bridges and all those other things, they all contribute to the ability for the community to respond and recover in a short period of time. And sustainability has nothing to do with that, right? That is to use the least amount of energy to develop that infrastructure is really the point of sustainability. And our 2050 goal of getting, our significant carbon footprint reduced when it comes to structures is a lofty goal and very difficult to attain, because we have to create the materials. We don't use bamboo to build buildings in the modern world. So everything that we use in a building is actually fabricated, and whether it be from raw materials to the final built structure, or recycled materials, or even parts of buildings reused, there's still all kinds of energy that go into that process. And if you were to design a building that uses the least amount of energy, as you might imagine, that optimization means you might have the least amount of material in the building, or maybe a material that isn't quite as ductile, right? That it goes through an earthquake and actually stretches a little bit and holds together, but is a much better material than something that might be brittle and fail early and potentially put the building at risk. Or maybe it's small connections that are made out of plastic that we use because we know that those small connections of these pipes that Erica talked about, when they're plastic, they can actually expand a little and move a little bit and won't damage the pipe as the structure that's supporting it moves a bit. And the sustainability response may say, well, that's plastic and it's completely a worthless input from a material standpoint into our process. The sustainability process is looking at what it is that you put in the building and kind of rating it and figuring out what its energy content is to create. It would be better if it were wood or if it were steel or something. And from a structural standpoint, that may not be smart at all. It may actually cause, in Erica's example, it may pull the pipe over when the brick falls over. But a plastic one might actually let loose. It's actually not strong enough to pull the pipe over because the pipe has more strength or more stiffness or something. And if we were to calculate that and figure it out and say, oh, well, we know that it's good and supported, but in an emergency, we're not going to create a problem. And so let's use this other part. So sustainability doesn't necessarily always comport well with resilience, and they're not the same. Some of the benefits are the building doesn't collapse and you don't have to rebuild it. So that's a pretty obvious way that, a resilient minded building, so one that is designed with resilience in mind, can get us back to normal with the least amount of energy input in that process. So clearly that can contribute to a more sustainable environment. However, like I said before, the big picture stuff is done. Like, we don't really have to worry about that anymore. So as long as we design a building that meets the building codes and they're being constructed using the materials that we specify, in the way that we specify that get built, should be pretty good. And that is not something that we really want to entertain. It is these small nuances that Erica's talking about that are most critical about that functionality. And again, they may not be compatible. So we try to separate those things out. They're definitely not the same. And even our engineering community doesn't gather that, right? They're trying to leverage sustainability's popularity and visibility and desire to kind of ride the coattails of a socially acceptable and maybe a large scale community understanding of what we do. So it's visible, it's shiny. We want to be attached to that usually. But it really doesn't make sense in the context of what Eric and I are trying to do, which is really change what it is that we do as structural engineers so we can provide the opportunity for communities to recover. And if you get the two commingled, you'll actually change the conversation. And we find that that's just, to us, relatively dangerous. So we try to be pretty consistent about saying that they're not the same, although in those conditions where they are, we can soften the discussion. But in general, it's just a goal for us to get structural engineers to know the difference and to contribute in a meaningful and intelligent way to that conversation, because most of this stuff about resilience is about planning, and sustainability isn't a whole lot different, although it can be held a little bit closer to a singular building. You can be very successful in a sustainability context on a building by building basis, but in a resilience context, that building by building needs to be large enough to affect the community or structure, right? I mean, again, it's not just buildings. So it's just the context of the planning discussion is different as well. And it's just, I don't know, Erica, how many people do you think know this level and kind of operate? It seems like it's about 15 to 20 people in the country are really knowledgeable of this at the planning level and are doing their best to kind of get everybody on board. So it's just a incredibly complicated concept. It's expensive, right? You have to think about this thing differently, and it's going to cost us a little bit more money, but we know that it costs us less money to recover. And Eric is going to talk about that a little bit. I think your question indicates, geez, we've lost a lot of money in fires, and same thing with floods, right? And we have more money spent on floods than we do almost any other hazard in the country. But how to prevent your building from being affected by floods? And if you've ever been to Hawaii, we know that we're going to get hurricanes there. So it turns out the bottom floor of buildings in Hawaii have been kind of sacrificial for a long, long time. This isn't something new for people that actually have to deal with this. So it's a concept that we understand. We just haven't attached a name to it. Now that we have, everybody wants to get on board. Nobody knows what they're talking about. So we're just trying to make sure that we're not saying anything too far out of the realm, because we want to be viable in that discussion and credible. And you got to know what you're talking about to be credible.
Awesome. Yeah, thanks for that clarification, Kevin. And like you were alluding to, yeah, we wanted to get onto the wildfires since we're all in California, or in the West Coast at least. I mean, I think you hear more about wildfires than you do about major earthquakes, especially this past couple of years. And yeah, it's something I wondered about too. Like we design for earthquakes, but then nothing really about fire, at least when I was going through school. So yeah, I did want to ask about this. And Erica, I'd like to talk to you more about the wildfire resilience. Each year, wildfires take lives, and they burn numerous structures. And just these past couple of years, yeah, I know whole communities have been devastated, and it has enormous economic and environmental impacts on the nation's communities and businesses. In your opinion, how did we get to this point of wildfire destruction within our communities, basically to where we are now? And just to add on to that, what existing resources are out there to protect lives and property in our communities?
I appreciate this question, because I think it's really important for us to understand how we got to today. So yes, we're seeing we have climate change. We have a lot of factors that are going into making this kind of perfect storm of disaster right now. And I think it's important for us to understand what got us to this point, so that we can understand how to change our behavior and move forward. So it's just kind of a crash course. It's really just like through the first almost three quarters of the 20th century, we as the US put out almost every single wildfire. That was the culture. Is there was a fire, we put it out. And it wasn't really until halfway through the 20th century that scientists realized that these fires actually help the landscape. It actually is beneficial to the ecology. It's beneficial to a lot of the animals in the landscape, and it's beneficial to a lot of the plants in the landscape. And so it took us, a few decades to change policies, but it really wasn't until the end of the 20th century that we started actually changing those policies. And now we really only put out fires when they threaten human life. But because our culture, first of all, was to put out every single fire, our forests became overgrown, and communities began to pop up close to wildland landscapes, or actually in wildland landscapes. And then all while climate change is creating these drought conditions and increasing temperatures. So we had this kind of incorrect approach to suppression. And then, we are the wildland urban interface communities, WUI communities, expanded rapidly. And then we have climate change on top of it. So now we're at the point where most fires threaten human life because of where our communities have grown and where they've developed. So now we're kind of still stuck in that same, we have to put out every single fire because of where our communities have developed. So when we're talking about, WUI resilience or wildfire resilience, it is actually very rare that a civil engineer or a structural engineer is involved in the conversation. And that's sort of where I see another massive problem. Forest ecologists are really great at their job of maintaining our forests and working around the confines of fires in a wildland landscape. But as Kevin talked about so well in answering the last question, we've been dealing with community resilience and working on the topic of community resilience for a very long time as it pertains to some other hazards. And so when we're talking about the resiliency of our communities, we're talking about hardening our infrastructure. You need to get civil engineers involved because we've been doing this for other hazards. We've been calculating risk for other hazards. So right now, kind of like we're at this kind of tipping point is how I kind of feel it, is that a lot of structural engineers are starting to think like, hey, we could do something about this. And we kind of know how to do community planning, as Kevin was talking about, just like the vast amounts of planning that we have to do. And, could we apply all of this knowledge that we've gained on floods and hurricanes and earthquakes over the last century, really, and apply it to the wildfire issue and the wildland urban interface issue? And that's so important because currently a third of our population in the United States lives in a wildland urban interface community. It's the fastest growing land use in the United States. So we have a ton of people who are at risk, and we actually don't even calculate that risk correctly. And so, without getting civil engineers involved, you don't have the people who have that knowledge about functional recovery, about community planning. We are so used to, in the earthquake engineering field, working with our partners and colleagues in public health, in public policy, in social science, understanding the value of our institutions within our community, like our schools and our healthcare and power and water. And we're used to designing around those important infrastructure systems. And it's just that the conversation hasn't included us. So I'm really excited that, more talks are happening, such as this one, where we're highlighting the need for civil engineers to be involved in the conversation, so that we can move forward, because really wildfire is just a hazard, just like earthquakes or floods or hurricanes or tsunamis really are. And so, I guess the next part of that question was, what are some existing resources that are out there? So because of this kind of shift in fire suppression policy, there was a significant amount of research performed throughout the 90s and early 2000s on defensible space and on fire resistant materials. All of that research was, or I guess I can never say all, but a vast majority of that research was incorporated into the National Fire Protection Association program within the International Wildland Urban Interface Code. So those are two amazing resources that communities can use to just start, or structural engineers can use to understand where to even begin. If communities want to start somewhere, they can start here. But mitigation for wildfire is not like an earthquake or tsunami or hurricane. You don't just do it once and then walk away. This has to happen every single year. So communities need to think about a sustainable long-term path on how to enforce mitigation, but also help out our communities and the residents of the communities for mitigation. Here in Oregon, I'm located in Oregon. Our Woi communities tend to be our vulnerable populations. They tend to be more low-income communities. And so, what do we do to make sure that everyone has access to a resilient community? That is just so important right now, and something we're struggling with on every hazard front. It's civil engineers to date, is making sure that we're providing options not just for certain portions of our communities or populations, but for everyone. And particularly, in wildfires, I talked about, the 2014 Napa earthquake, how we saw, one damaged building caused threat to another building that may have been retrofitted or wasn't damaged. We see this on an even larger scale in wildfires. If you mitigate because you think it's important or you have the resources to do so, but your neighbor does not have those resources, then you've maybe reduced your risk by a little bit, but you haven't completely eliminated it. So we are so dependent upon our neighbors and the full community buy-in and involvement when it comes to wildfires in order to mitigate. And communities, and I think this is where communities really need to come together and think outside of the box, and pull from those mitigation strategies and community planning strategies that have been implemented for these other hazards.
Yeah, that's yeah. I like how you guys touched upon the communities about resilience, because it doesn't really matter if you're the only house that didn't get burned down. I mean, there's no community at the end of the day if the whole community wasn't involved. And I think that's a great point, that it's not just one house that we can mitigate or help protect during a wildfire, but it really does extend to the communities, because I mean, at the end of the day, that's what we want to protect, not just one single building. And it's we want to help those recover quickly. And in terms of mitigation, kind of structural engineering, were you thinking just I'm thinking just off the top of my head, is it like clearing the brush fire or clearing the trees around an area, or what are some mitigation techniques that because I'm not too familiar with that. I'm kind of wondering if someone asked me, hey, you're the structural engineer, what can you do to help prevent forest or help protect my house against the forest fire? I think those are some good resources that you sent out, but do you have any examples of those mitigation measures?
So maybe like this is fire can spread to a building in one of three ways. So the first way is, like direct vegetation contact. So this is why, we talk about like, don't store your firewood right next to your house, right? So, your firewood catches on fire, it's touching your house is going to catch on fire. Okay, so that's one way. Another way is embers. This is actually the number one way that fires can catch, that homes catch on fire is through embers. So it's actually not there's like a big misconception that the big flames are, spreading the fire around the community. That's not it at all. It's actually the smaller flames and it's embers. And so, the issue with embers is that the fire might be quite far away, and the embers or firebrands can land on your roof or land near your house, and then catch fire to any combustible material there. If your roof is made of a combustible material, that will catch fire. Okay, so that's why, fire-resistant materials are important, but also, cleaning around your house within like 0 to 5 feet of combustible material, because that's how, if something catches fire within that in that region, then it can spread to your home itself. And then the last way that fire can spread is through radiative heat transfer from surrounding structures. All right, so that's like kind of pretty rare in a wildfire, because usually woolly communities, homes are really spread out. This is really how fire spreads in a city. So if you had like a post-earthquake fire in the Bay Area, this is how fire would spread around. So it's in the Fireways program, there's actually 3 zones. And in the first zone, it's at 0 to 5 feet of like clearing all the combustible material. And then you can have, it basically between your home and 100 feet, there's a gradation of, clearing. And really that is so that if the fire doesn't have any fuel to burn, it can't burn. Right. So, your candle, like, once it burns to the end, it goes out because there's nothing else to burn. So if you don't have any fuel for the fire to consume, then it will stop. It will fizzle out. So this is another reason why when fighting fire, you see like firefighters get ahead of the fire front and set another fire. They actually start fires so that they burn up all the fuel, so that when the wildfire front comes in, there's no more fuel to burn and it stops moving. So like, just like thinking, I mean, we're very logical people as engineers, right? So, like fuel is a big thing. Like thinking about if you have combustible material, that will fuel the fire. And something that happens quite a bit in wildfires is actually the fire front will move on, and you have smoldering of combustible material, and that smoldering actually catches the house on fire. So you'll see homes being like catching fire and burning even after the fire has moved on, like hours and hours later. So like fuel is really the biggest thing. So like any combustible siding, any combustible material on your roof, combustible material around your house, this is what is going to cause fires and cause your house to catch on fire. And once the fire gets inside of the building, so if we kind of like switch gears for a second, we think about like engineered buildings, like schools or hospitals or something a structural engineer is involved with. Once the fire gets inside the building, so either through broken windows, either through vents, or like you have a combustible roof and it collapses, and now all of a sudden, the fire's inside the building, it behaves like a building fire. So this is why, structural engineers who work in the field of structural fire engineering are important to be involved, because this now kind of goes back to, okay, well, how does a steel building behave in a fire, or a concrete building behave in a fire? And how can we make sure that the fire doesn't spread rapidly throughout the building? How do we make sure we've contained it? And how do we make sure that the building doesn't collapse or isn't heavily damaged after the fire or during the fire, so that we can get people back into the building and repair it and get the community back up and running? Sorry, that was kind of a long answer.
No, that's great. Yeah, I learned a lot. And like you're mentioning too, I know there's work going into the performance-based design of fire hazards too when buildings are burning. So it's there's a lot. It seems like there's a lot more that we can learn and get into as structural engineers and as communities. Kevin, can you provide some examples of both successful recovery or resilient cities following a major event, as well as some less desirable recovery scenarios?
Sure. My interest in resilience actually came from exactly what you're asking here, is that there was a major earthquake in Tainan, Taiwan, and I can't remember the date. I want to say 2017, 2016. And Tainan is an amazingly large city. I had not traveled to Asia much, but here in California, it looked a lot like Sacramento in terms of landscape, very flat, a few very tall buildings, and then just huge amounts of sprawl. But Sacramento stops, it doesn't go on for miles and miles. And Tainan goes on for the downtown portion, probably maybe 6 to 10 miles in each direction. It's just a huge amount of buildings, if you will. And then there's buildings kind of all over the place, just like anywhere. And there are hills and things like that. So we decided, we as a company, Simpson, Gumpertz, and Heger, and we decided to go review the earthquake. It seemed large enough, and people were talking about it as, hey, we ought to, dip our toe into it. I don't necessarily love that because it's a horrible thing to go through an earthquake. There's lots of things going on. They don't need a bunch of engineers sniffing around, and there were already teams there looking, at it from ERI and other associations that do quite a bit of great data gathering and writing papers and education, right? And that's the process that we go through. And so as we were there, there's a couple of major collapses that occurred, made world news. I was going through this normal process, like go to a collapsed building, figure out why it collapsed, try to develop some lessons learned, and so I could share it back with the rest of our company and potentially, whether it be clients or associations and all the rest of it. And it was kind of the same old story. And I hate to say that because but I've been practicing for 25 years. And when I first started, it was actually in February of 1995. And so we'd had the 1994 Northridge earthquake and the Kobe 1995 earthquake. And those two earthquakes changed the way that we deal with earthquakes as structural engineers. So ever since I started working or was in graduate school, I have been aware of how to do things differently about earthquakes and all of the standards that we use. I was there when they were first developed, and I've watched them grow and evolve over time. And so I know what 25 years of development and standards looks like. So I wasn't too surprised because I've been part of that whole study group. And my colleague that was with me, he's incredibly brilliant, a Ph.D. and really knows buildings and phenomenal analyst. We're standing next to this building that's partially collapsed, and he says, "We're not really learning much." And by then I had kind of put things together, and I said, because you're looking at the damaged building that's in front of us, I want you to turn around and look at all of the buildings that are not damaged and look at how we got here and the train and the airports that are there. And it isn't that, the buildings and the infrastructure are miles and miles of communist-based development. All right, there's a whole bunch of very regular buildings that go and are funded by the government, and they're not very well built. Not because they're incapable of it, but they just have to spread all of this construction over many, many miles, and it takes a lot of resources. So they build as well as they can with what they have. And they weren't horrible, but they definitely didn't have things that we would put in it. They had unreinforced masonry interior walls, like Erica was talking about in that hospital in Mexico City, very common throughout the world. Some situations where you'd say, oh, it should collapse. And they really didn't. And it's primarily just because they are miles and miles long, and earthquakes just kind of shake stuff and move along, and they survived, just like the wildfire stuff that Erica was talking about, and no embers came back and caught them on fire, if you will. So I noticed that all of that was there, and like, wow, okay, that's surprising. But they also had a culture that allowed them to recover, really forced them to recover very quickly. So these buildings that collapsed, it was really about cleaning them up, getting them out of the way, and making sure that the roads were functional, make sure that the water mains were repaired, to make sure that people felt like they could actually get back to normal. And one of the major contributors to that is they had a huge water main on the order of 3 meters in diameter, just this gigantic pipe that had ruptured at one end of town, I'll call it. The city is big, but it was kind of in the main part of the city. And they determined where it broke, and they immediately dug into the ground, found that pipe, got huge sections of pipe, realigned it, basically brought it up above ground, and ran it for 7 miles down the center of this major thoroughfare in Tainan. And it basically maintained water delivery to all of the people in the city, an incredibly disruptive way, right? You run this pipe across this long highway, and you have a bunch of roads that cross the highway. They didn't have bridges. And so you couldn't get across where the pipe was. And so people just said, oh, okay. And they all drove down to where the pipe kind of went back underground or turned. I can't remember what happened to it. And they would hang a U-turn and then come back to where they needed to go. And nobody was complaining, as far as I could tell. They weren't, protesting. It was just like, oh, we have to do this to get back and going. And we were there, I think, 10 to 12 days after the earthquake. And it was amazing how functional everything was. We were in a hotel and things were kind of normal. There was food there. People were going about their business. We saw the government kind of dealing with these adjacency buildings that Erica's talking about, that they could not, basically run their business. And the government, and within days, had identified that they were affected negatively and gave them basically recovery money that says, look, you're missing out on, $2,000 a day. And so it's been about 20 days. So, here's $40,000 and this should cover you for now. And the people were like, great. And they could continue to live. It was a completely cultural response. And it was how we were talking about communities recover. That was part of it. It wasn't the infrastructure. It was how the community responded. And it was very much driven by the 1999 Chi-Chi earthquake. And we had talked to enough people that we learned that they had learned so much about their buildings and how to recover and where their biggest risks were, that they went after their schools and rebuilt schools, or retrofitted schools. And we saw how that actually performed very well and really helped them in Tainan. And then how they could recover, their whole planning process. Earthquake happens, what do you do? And it was very active. And like Erica said, in the wildfire world, you have to do something on an annual basis. In the successful earthquake resilience world, you also have to practice how you're going to recover, because it's not something that you just do naturally. So that was an incredibly instructive and I would call it successful resilient response for a community, and a very large community at that. What was interesting at the time, I had given a couple talks and I think it even started to develop, or maybe developed a paper on it. I compared it to Christchurch Recovery that was happening at the same time. It was probably about a year or two into the recovery at Christchurch. And we were doing work there, and I had seen that. And the downtown Christchurch area, of course, was decimated in that earthquake. There were significant collapses, but a number of buildings did well and had adjacent buildings that weren't doing so well. And it was deemed that too dangerous, and so they cordoned off the central building district, excuse me, and they really couldn't figure out what to do with those buildings. And then their insurance environment was such that they could actually vacate them and say that they were unoccupiable and get full replacement value of that building. And for an owner, that's a nice thing. And so there was no impetus to actually help the community recover. And it's not that those people are bad or they, were evil and wanted to make a bunch of money. They just had a building that had plenty of damage. It didn't fall down, but it had plenty of damage. And to recover, they would have to take that money and then rebuild it. And there was no community, like you said earlier, right? You said, if you're the only house to recover and there's no community, why would, now what do you do with that house? And we had very large buildings in Christchurch that kind of went through the same thing. And so just, from a survival standpoint, the entire city kind of went, I'll call it one ring outside of Christchurch. And so there, most of the people that had businesses and wanted to maintain a normalcy in life kind of moved out of the central building district, to the I'll call it foothills of the suburb. And then over time, as it started to grow and fill that in, you got another ring worth. And so Christchurch kind of recovered on its own for the first 5 to 10 years by moving where things were happening. And they didn't have this core central building district. And what they had to do, business district, excuse me, I say building, but it's called the central business district, as a government, is actually put a whole bunch of money into some government facilities that were damaged. And so they rebuilt what they call the Justice Precinct, and it was an entire city block related to how they actually deal with justice. And so there was a jail, and there was City Hall, and there was a courtroom and all that. And so it was all on this very large plot, and they isolated the whole plot. So it's kind of a super civil engineering response to, how do we fix this problem? Well, we isolated an entire city block, and they did it very well. And it was a massive project, but they were done. The largest hospital, they actually funded significantly from the government and got that into place. And the idea was not like we need these things because they weren't functional after the earthquake. It was basically to encourage recovery back into the central business district. And so the community then decided and understood that we have to recover in this manner. And so as I've worked with resilience, I've actually discovered that that wasn't a failure. It was actually what we do as a community is we just survive. And so their survival made things change, and it was a little bit different. And then it's evolving into what is going to be a different city. And that ties into this concept that we're working on now, which is adaptive resilience. So we at that time thought, oh, you're not back to normal. So it wasn't a successful recovery. Well, the reality is as a community, they decided we're not going to get back to normal. That's okay with us. We just don't want the city to disappear, and we want those people that are devoted and kind of tied into Christchurch to have a place to return to. And so they had adjusted their targets and their timeline, because there's what we call a resilience recovery graph. The event happens and the functionality of the space drops precipitously. So if normal is a flat line, it kind of has a big dip. And then it slowly has a slope to come back up to that line, that flat line that existed before. And that line that exists kind of after the slope ends and it gets asymptotic to kind of normalcy, that can be in a number of different places. And as structural engineers and civil engineers, we say, that line should go up. We should have more functionality or more ability to kind of do things in that city. And it doesn't make sense most of the time because, it was fine before and everybody was happy with it. And most of the community doesn't want to be better. What they want to be is a little bit more robust so they don't have to actually repair as much and it doesn't take as much time to recover. So really what they want is they want a bunch of these curves all put together. And when they recover, they want the next curve to look very differently. They want it to drop, maybe as little as possible, but it drops. And they want the recovery curve to not be linear and take a long time. They want it to be hyperbolic and just go whoop, right up to the top and get things back to normal as quickly as possible. So watching those two cities recover in terms of earthquake damage was very, very instructive. And I've been kind of preaching this for a long, long time now. So, and it's approaching 10 years or so that we've been thinking about it. And it's of course just related to earthquakes, but we have so many tools and I have so much knowledge there that it's easy for me to articulate that. Erica's work in wildfires is just so important because she's at the stage where we were probably in 23 or so, where we're trying to figure out what an earthquake is and how to measure it and how to design for it. And so that, it tells you we've come a long way in 70 years. Erica, will probably still be here with as much energy and vitality trying to get us to do something 70 years from now. But we just have to build that knowledge up and then kind of adapt what we do to it as civil engineers and a community to make ourselves kind of, survivable or existing in a comfortable way in face of all of these hazards. And the same thing is happening with flood and hurricanes and even wind events now, tornadoes and that kind of thing, is we're recognizing that, well, we took care of earthquakes, let's go after the other stuff. And that's really what the building code development community is doing. Most of us in leadership positions around associations and even the government that has some ideas about it are really trying to figure out how to mitigate so that we don't spend money on recovery, because it's on the order of somewhere between 5 and 10 times the cost that would take to mitigate. And if we're smart, we spend that money ahead of time to save money in the long run. However, we're the US and we like to spend money now, and then we don't think about spending money in the future. Just look at our credit card bills. And so the reality of that is, as consumers and people really impede that. And that's why it's so important that you have things like this podcast where we can kind of spout off about things we shouldn't be, but we understand how it fits in the bigger picture. And we really like for people to kind of think about it along those lines.
Yeah, that was great. I completely agree with it's the education part too. And what you were mentioning about how the communities, like you were saying, I think culture for sure has a big part of it. Like that first example where it was kind of just like, hey, we need to fix it. Let's fix it. Whatever we need to do, fix it. And if the whole community's there, great. But then you have that other example in Christchurch where it was kind of just like, I guess, kind of governed by the way the government responded or how that building responded. Kind of just like, hey, that building's kind of damaged. Let's kind of abandon it. And so it kind of brings business out of that, but that whole area gets affected because maybe that was like the bustling building for that.
Yeah, it was very unique. It had twofold conditions that don't exist anywhere else. One was the insurance industry, and the recognition that if you went in and just fixed buildings, you would actually probably put yourself at risk at actually just buying that repair without ever having anybody compensate for it. So that it was better to say the building was damaged beyond repair, just like you would like with a car, getting the car towed versus trying to fix it. So it was really that kind of mentality. And then looking at what was not safe and trying to figure out what to do with a high rise that's 5% to 10% out of plumb. How do you get that back plumb and safe for all the other buildings around it in the event of some kind of aftershock? And you have to remember that the Christchurch earthquakes were actually 2 earthquakes separated by a year of very similar magnitude. So you had a community that was just freaked out appropriately that said, well, I mean, if it looks like it's going to collapse, we have to think another earthquake's going to come along and collapse it. And so they weren't doing anything different than any other community would, but they had this little insurance piece to it and the way that businesses operate that made them pause. And when they paused, they had to think about it a little bit in a bigger context. And I think that those kind of instigators are very important. And so Erica can't talk for another 2 hours, but I wish she could, because you guys could hear this a little, which is really important. After wildfires go through major developments, insurers pull out, and they actually won't insure new houses that are built there. And so people don't want to build a house where they're not going to have fire insurance where a fire has occurred before. And so it really decimates the ability to recover in the same spot. And we're having that in a few communities in California. And it's not really the large communities. Sometimes there's enough governmental pressure that insurance companies will come back in. But it's these little buildings that are off in the, deep in the woods, like Erica said. We're putting a lot of development inside of forests themselves. They are unable to insure their home. And if they find out they're unable to insure their home, they're very reluctant to rebuild there. And so now we've reduced the opportunity to rebuild, which is not going to help us recover. So there's lots of interesting influence that we have to be aware of as structural engineers if we're going to speak intelligently and try to help guide this planning discussion, because we understand the buildings. It's like, yeah, you can build it, and you can build it better, and you can build it with better materials, but there's these social ramifications and actually ownership ramifications that you might want to consider. And we don't think about that a lot, right? Most of us go to work, do what we're assigned, look at a building code, make sure that we meet that, get the permit, try to keep up with the contractor, and the building's done, and we go to the next one. It's very, very hard to think bigger picture and contribute. But when you ever get that opportunity, you want to make sure you got the right tool at your disposal so you can bring it out and use it the best you can. And I think that that's really the best way for structural engineers to get involved, is to get knowledgeable. And it's going to take more than just listening to Eric and I, but it's really just about knowing how to speak when you get the opportunity.
Yeah. I think also, like, when you're talking about the culture, like, it's a lot of when I talk to my students and I talk about resilience, reality. In Tainan, when you're talking about like the residents who are just driving around the broken water main, there's an expectation that yes, we're going to have disruption to our lives. I do think this talk of resilience means no damage is harmful, because there are very resilient communities that are completely wiped out every time there's a flood or a fire or an earthquake or name your hazard, and they just rebuild. And their expectation is that yes, we're going to be wiped out, and we're going to be ready and to rebuild, right afterwards. So I do think that as structural engineers, we all have those friends that on the West Coast that are like, my building's earthquake proof. And I think we've all heard it, right? But I think it goes, a lot of it goes to like, what is the society's expectation of how their community is going to actually behave in one of these hazards? And then what's the reality? And making sure that people are aware that when we say 10% of the buildings are going to collapse or be heavily damaged, that seems like such a small amount. But if you think about a city like Los Angeles, 10% of the building, like that's a lot of buildings. So, really making sure that we're speaking in terms that the public understands. And just like kind of like going back to wildfires, like we can't stop the wildfire from encroaching on the community. It's like trying to stop a hurricane from making landfall. It's not going to happen. But we can make sure that communities understand what's going to happen in a wildfire. That, if you have homes in certain areas, you're going to have a higher likelihood of them burning down. Or if you mitigate and your neighbor doesn't, how does that affect your risk? If your neighbor mitigates and you don't, how does that affect your risk? Like we have to be able to communicate with these communities that are located in these high hazard areas or hazardous areas so that they can make plans, right? Just kind of going back to what Kevin was talking about with resilience, it's all about planning. And it's not planning for no damage, because that might be, we might see little damage in our newer buildings, but the vast majority of our buildings are existing and not built to the latest building codes. So how do we plan for that there is going to be damage? Where is there going to be damage? What communities are they going to impact? And how can we, like Kevin was saying, how can we plan for that now? Even in, in mitigation, but also in making sure that we're ready to deploy aid, water, financial resources, shelter, whatever that means, to those, sub-communities in our community, to make sure that we can get them back on their feet and that they can go back to their job.
Yeah, thanks, Erica. I know, for me personally, this is, yeah, like what you guys are saying. It's not just the building. As structural engineers, we typically just, hey, building, like you were saying, Kevin, get it out, permit, done. And yeah, we design it for X amount of drift, and if it's X amount of drift, great. But what happens if it does, and then your tower's leaning? What do you do about it? I think that's a question that those cities, those examples, have learned from, that they've experienced, and they're learning from it. I think kind of well, I guess over here in the West Coast, I think it's more about wildfires that you see, and because none of the major cities get affected by large earthquakes that much, at least in terms of major cities like LA or whatnot. But it is a good point about the public knowledge on what their buildings are designed for, and letting them know that, yeah, it's not earthquake proof. That's a great point. A lot of people think their buildings are earthquake proof and whatnot, but I try to explain it like, well, not really. It's kind of like your car. Your car can take small bumps and bruises, but if it gets in a big accident, you got to replace it, or it's gonna you can't use it. And that's what our building codes are at this point. But a lot of people don't know about that, or even have the earthquake insurance like they do with cars. So I do think there is that big gap of knowledge, and talking about it like this too, letting I'd like to get the structural engineers more vocal about it. I'd like to get it more mainstream, because I talk to a lot of non-engineers too, and that's one big misconception that they don't know about. So even with the wildfires, and my last, I guess, observation or comment was, I know both of you have been to those sites where after disasters have happened, and it's from talking to other people that have been to those sites, even with the wildfires. I think I saw someone present about his reconnaissance when he went to a wildfire. I mean, it's not just the buildings, it's really the communities that are affected. It's not just, like you were saying, kind of, Kevin, like, oh, let's just go engineer and kind of geek out about how this building collapsed. Well, no, that wasn't a building to them. It was their homes. It was a community. And, as engineers, I think if we take take a look at that bigger picture, I think that's great. Like doing the education about, hey, what can we expect, and what are the expectations? And I think as engineers, if we can take that bigger picture, not just about the buildings, I think that's great. Kevin, I had my last question. How can structural engineers get more involved in resilience discussions?
Yeah, so I have a plea. Really, it's about the profession itself. Is that we've spent so much time, energy, and knowledge on our building codes, that it's almost for especially new buildings, it's almost a technician's job now. There's not a lot of creativity that you're allowed, which is okay. And we have very, very robust vendors who are actually kind of filling in for the things that we had to do 20, 30 years ago. And so it's much easier to build, to design and build buildings. And so the classic structural engineering things that we understand and know and have to learn, we don't apply in the same way that we did when I first started my career. And as Erica indicated, when she talks to her students, she says, hey, there's all of this other stuff going on. And I just, Eric, I don't know, I can't remember how Erica stumbled onto our committee, but it was so great that, there's a bunch of Ericas out there, because that's what it really has to happen, is that we have to start at the undergraduate education level and the graduate education level, that as you pursue a career in civil and structural engineering, you have to recognize that you're valuable in a different way, not in what I always refer to as WO²/8. I mean, this is just, plug and play. It's not difficult. It really doesn't challenge us. It doesn't use the best and brightest minds, and it won't attract the best and brightest minds. But if you step out of that, and things that you can add to in conversation, but you have to we actually can move the needle and educate yourself differently. And Erica's mentioned it a bunch of times, and I haven't, but it's something that I spent a pretty significant amount of my career on, which is the ability to understand and calculate and apply risk. And that is, go study your statistics, understand exactly how the math plays into our society. And it does in everything that we do. The way that insurance premiums are established, or whether or not they're going to insure buildings or not, are based on a big numbers game, that they have enough diversity in their portfolio that they decide that we're not going to change anything. You do something special to your building, you don't get a break on your insurance, because if it does well, they're going to take your money and spend it on one that doesn't do well. And that's part of the plan. And if you don't understand that, then you miss out on that bigger picture. And so I've spent a lot of my career explaining to people that are, designing and building a brand new building. They say, so how much earthquake insurance do I need? I said, none. And the reason you need none is because the deductible is so high, that means that you're going to have 25% damage on your building. And we know that it's actually around the order to 10 to 20%. So you'll never do anything but pay for your own damage, and you're going to lose all that money, on earthquake insurance, and over a long period of time. So you're going to hang onto that building for 50 years. Please isolate it or use some higher technology to decrease the damage to those internal components and those non-structural elements. That's really going to be far more effective to save you money over the long term. You have to pay a little bit more upfront, but away you go. And it's exactly the conversation that we had with vehicles with airbags and with seat belts and all of those things. Like, it's going to cost me more money. Yeah, but down the road, you're going to save tons of money. Making them cheaper and more energy absorbent wasn't because manufacturers were being cheap and they didn't want to lose money. It was because it was just a better way to deal with a problem that we could make worse. And there's a really great video, go find it on YouTube, where in 1960s, I think it's like an Impala hits like a Toyota Camry head on, and the Camry just kind of crumples up, just like we've seen a bunch of times in horrible accidents where people walk away. But the Impala turned into a bunch of big plates and shards that shot through the cabin of the car. And you just look and think, okay, that's clearly why people died in head-on accidents, and they don't really anymore. It's just a change in the engineering, how it's applied to the situation. So we, as structural engineers, need to get more involved in understanding risk and how to actually calculate that and apply it to what we're working with. And I'll leave you with this thought because it's important. And if it sears itself in your brain, you're going to be far more interested in a cocktail party, or far more hated at a cocktail party. So earthquake risk is always driving what people want to do with their buildings where I practice. And we just try to get people to understand that and potentially utilize our expertise to give them a better chance at survival over a long period of time. And we figured out all kinds of ways to influence that, whether it be building codes or flashy introductions, if you will. But what's really interesting is the actual numbers, the numbers that we use as engineers, put in front of them in context with their world. And so these are CEOs, CFOs, people that work in a business environment. And that's really what buildings are, is they're a financial vehicle for the most part for these commercial buildings, and obviously not houses and housing and that kind of stuff. So in the Bay Area, we have the Hayward Fault. And the Hayward Fault, I'll just use round numbers, a 1% chance of a magnitude 7 on an annualized basis. So there's a different percentage over a long period of time, but if you look at that on an annualized basis, you got a 1 in 100% chance every year that big event occurs. That's just how we work our probabilities, and it's the basis for our hazards and all the rest of it. Then we design our new buildings to have a 1% chance of collapse in that level event. And so if you multiply those probabilities, you know that 0.1 times 0.1 is far less than any risk that you would ever consider on an annualized basis in context with your business. And it turns out that it's significantly lower than the risk of having a global economic collapse. So the risk for this person's building to collapse and actually to do something greater than the building code is less of a concern to them than having the entire world economy collapse on an annualized basis. We have no power to influence them from a business or financial standpoint. We have everything to influence them from a community response standpoint. And what happens is that we have to be knowledgeable enough to explain to them. So if you're not going to do it for a business reason, that's fine. But you need to do it from a functionality standpoint, which means it's going to be damaged enough, not collapse, but damaged enough that you can't get into it and use it. And so you have to turn the discussion into functionality, just like Erica talked about. That's the key, and that's the game that we have to understand and play. And that means we have to know non-structural systems. We have to know our statistics. We have to know how we develop our building codes. We have to understand all of that influence so we can pivot and actually help influence people's decisions so they positively affect themselves and the community around them. And if we don't do that, then there's no impetus for them to do anything different until we make laws. And then everybody feels like they're being, forced to do things, and there's huge pushback. And as soon as there's huge pushback, that's about money, and the people with more money win. And right now, of course, all of us are engineers, structural engineers. We know that we don't have enough money to win, so we're not going to be very successful in that battle. We have to get people kind of in a grassroots sense to understand this is really important, and work on everyone to understand this is what we want to have happen, and figure out ways that it makes sense for everybody. And that just means that we as structural engineers need to know that when, so Erica has some juniors and seniors, she's working hard on them so that when they graduate, they'll have a structural engineering degree, whether it be undergrad or graduate. Hopefully they go through graduate school and can kind of get all that basic stuff done. She's trying to educate them to know more than just WL²/8. Let's think about all of these other things. And this is what I want you to go into the working world with, is a knowledge of the hazards and a knowledge of how we develop our building codes based on probability of hazards and how to calculate risk and apply it to your situation. And if we get more of that to occur, then the structural engineering profession changes, and we have a totally different message to deliver, and we become far more valuable. And so for me, as a leader of structural engineering associations, that's what I want to have happen. I want us to be like doctors, like, oh, we need these guys, and they're very valuable, and of course I would pay higher fees for them. That's important. And it's important because if we keep going the way that we're going, we're going to turn into a bunch of technicians, which is very much like it's, the auto world, right? They used to have to be a certified technician and all these other things. And now it's, they're just kind of kicking around, and they're, reasonably well managed, but anybody can fix a car. And so you have all kinds of competition, and typically you don't care because your car is fungible, and then you move on to the next thing. We want it to be, we are important for a long period of time, and we're attached to buildings and infrastructure that needs to exist for much longer than 20, 30 years. We're talking about 50 to 100. So awesome. That's how we get involved, is think differently, and don't be complacent and think you're just going to get a job where you're churning designs. That's not going to help us at all.
Yeah, it's not just that calc that you have in front of you. I mean, I really like the way both of you expanded the problem. It's not just, hey, what's the deflection of this beam? It's, hey, take a look at the bigger picture, and not just that, but also understanding different aspects of it so we can explain it to our clients, to communities, and show them that, we can do more than just calculate a beam, really provide, but it takes us to go into it and, use our engineering skills to solve these problems, these bigger problems, community problems that I think are, a lot more than just the building. But when you look at the community as a whole, really important problems that communities go through. So thanks for that, Kevin. Thank you so much, Erica. I really appreciate you coming on here and talking about this. I know this is a really interesting topic, and I appreciate your expertise, and just thanks for coming on.
So happy for the opportunity.
Yeah, thank you.
I hope you enjoyed the episode today. We'd love to hear your feedback, comments, and or questions. To leave them, please visit structuralengineeringchannel.com. There you'll find a summary of the key points discussed in today's episode, which is episode number 51, as well as links to any of the resources, websites, or books mentioned during this episode. Don't forget to subscribe on Apple Podcasts or wherever you listen to your podcast. Until next time, we wish you the best in all of your structural engineering endeavors.